Some objects in the universe do not shine, do not speak, and do not need to move toward us to feel overwhelming. A black hole can be the corpse of a star, the hidden heart of a galaxy, a ripple-making pair spiraling into one, or even a theoretical shadow from the first breath of the cosmos. Each type reveals a different kind of darkness collapse, hunger, scale, silence, and the strange places where physics begins to lose its familiar shape. If this kind of calm cosmic mystery helps make your night a little deeper, feel free to like the video, subscribe for more quiet science journeys, and share it with someone who loves space at a slower pace. Thank you for spending your time here. Leave a comment with where you're watching from and what time it is in your corner of the world. Now, let us step gently toward the edge of the event horizon and begin. A black hole begins with a boundary rather than a surface. There is no solid wall waiting at its edge, no shell that can be touched from the outside, no visible skin marking the place where ordinary space ends. The border is an event horizon, a limit drawn not by material but by gravity itself. Outside that limit, light may still travel outward, signals may still escape, and matter may still turn away if enough speed and direction remain available. Inside it, every possible future points inward. Escape is no longer difficult. It is no longer expensive. It has disappeared from the geometry of space-time. This is the first reason black holes feel so severe in the scientific imagination. They are not merely heavy objects. They are regions where the structure of motion has been changed so deeply that the universe no longer offers an outward path. The fear associated with them often comes from images of cosmic hunger, but the deeper unease is quieter and more precise. A black hole is what happens when gravity becomes not just a force pulling on matter, but a condition that decides what the future can contain. General relativity describes gravity as the curvature of space-time, and in the presence of enough mass compressed into a small enough volume, that curvature can close around itself. The event horizon is the sign that this closure has occurred. It does not shine, because light crossing it cannot return. It does not announce itself as a surface, because an object falling across a large horizon might not feel a sudden impact at that exact crossing. From far away, however, the difference is absolute. A signal sent from just outside can still reach the wider universe. A signal sent from just inside cannot. The boundary divides what can be known from what can only be inferred. That distinction matters because black holes are both physical objects and limits on observation. Their existence is known through everything around them. The stars that orbit too quickly around invisible mass, the gas that heats as it spirals inward, the gravitational waves released when two of them merge, and the glowing rings of matter that reveal the shadow of the horizon itself. The darkness is not empty. It is outlined by consequence. The simplest way to form a black hole is to compress enough mass within its Schwarzschild radius, the critical size at which escape speed reaches the speed of light. For the Sun, that radius would be only a few kilometers. The Sun is nowhere near becoming a black hole, because its mass is spread through a glowing sphere far larger than that limit. But the comparison shows how extreme the compression must be. Matter is not just packed tightly. It is pushed past the last stable arrangement known to ordinary astrophysics. At lower densities, stars can resist gravity with heat from nuclear fusion. Dead stellar cores can resist with quantum pressure. The strange support created by particles that cannot be squeezed into identical states. But beyond certain thresholds, these forms of resistance fail. Gravity continues, and the familiar categories of matter lose their ability to hold shape. What remains, from the outside, is mass, spin, electric charge if any survives, and the horizon that hides the interior from direct view. The interior itself becomes one of the deepest problems in physics. Classical relativity points toward a singularity, a place where density and curvature become infinite. But infinity in a physical theory is often a warning that the theory has been taken beyond its proper range. At that point, quantum physics should matter. Yet a complete quantum theory of gravity does not yet exist. The black hole therefore stands at a strange intersection. It is one of the most confidently observed predictions of relativity, and at the same time one of the places where relativity appears incomplete. This is why even the definition of a black hole carries a hidden tension. The horizon can be described with great mathematical clarity, and its effects can be measured across the sky, but the final interior state remains inaccessible. The universe allows the outside evidence to accumulate while keeping the central answer sealed. Not all black holes, however, press on reality in the same way. Some are born when massive stars die. These stellar black holes may contain several to many times the mass of the Sun, yet their horizons can be smaller than a city or a small region on a planet. Their danger is local but intense, close enough. They can tear gas from companion stars, heat that gas into X-ray brightness, and bend nearby orbits into shapes that reveal an unseen center. Others occupy a quieter middle territory, intermediate black holes, if confirmed in large numbers, may weigh hundreds, thousands, or more solar masses. But they are difficult to locate because they are often not feeding brightly and may hide in dense star clusters or small galaxies. Their importance lies not only in what they are, but in what they may explain. They could be missing steps in the growth from stellar remnants to the largest black holes known. Above them are the supermassive black holes that sit in the centers of galaxies. These objects can hold millions or billions of solar masses. They are not simply enlarged versions of stellar collapse. Their formation is tied to the history of galaxies, to flows of gas, to mergers, and to conditions in the early universe that remain under study. Around them, matter can form luminous disks and jets powerful enough to influence the birth of stars across an entire galaxy. The black hole itself is dark, but its surroundings may become one of the brightest engines in the cosmos. At still more speculative levels, the hierarchy becomes stranger. Primordial black holes may have formed before the first stars, created by density fluctuations in the hot young universe. If they exist, they could span a wide range of masses, and some versions have been considered as possible contributors to dark matter. The evidence remains incomplete, but the idea changes the age of the black hole story. Black holes would not only be the graves of stars, some could be fossils from the first moments of cosmic history. Then there are quantum black holes, hypothetical objects so small that their meaning belongs more to the search for a unified theory than to ordinary astronomy. At such scales, the event horizon becomes a meeting place for incompatible rules. Gravity demands one description. Quantum mechanics demands another. Neither alone is enough. Even a theoretical black hole at that scale would not behave like the slow, massive objects found in galaxies. It would evaporate through Hawking radiation almost immediately, if the theory is correct, leaving behind not a visible monster, but a clue about physics at its smallest and most difficult boundary. These categories make the word black hole deceptively simple. It names a family of objects and possibilities that range from collapsed stars to galactic anchors, from possible dark relics to mathematical hints of physics not yet understood. What connects them is the horizon, the point at which escape vanishes and the ordinary exchange between object and observer is broken. What separates them is scale, origin, environment, and the evidence available for each one. A stellar black hole can be studied through a companion star. A supermassive black hole can be traced by the motions of stars near a galactic center, or by the glow of infalling gas. A primordial black hole might reveal itself only through a brief gravitational lensing event, or a faint trace in cosmic statistics. A quantum black hole may never be directly seen at all. The most unsettling types are therefore not always the largest. Some terrify through scale, some through density, some through invisibility, and some through the way they expose the incompleteness of human theory. The event horizon is the common threshold beneath all of them. It is the first step in the ascent, the quiet line that makes every later category possible. Before the stellar corpse, before the hidden middleweight, before the galactic engine, before the ancient relic and the quantum abyss, there is this one idea: space-time can be curved so deeply that it closes a door behind anything that crosses it. The terror is not that black holes roam through the universe like predators. Most are distant, stable, and detectable only through careful evidence. The terror is that they are natural. They arise from the same laws that make stars shine, galaxies gather, and planets hold their shape. They are not violations of physics, but consequences of it. That is what gives the hierarchy its quiet power. Each type is a different expression of the same underlying fact. Given enough compression, enough gravity, or the right conditions in the early universe, reality can produce a place where light itself has no outward future. The journey through black holes begins at that threshold, because the event horizon is not merely an edge in space. It is the first sign that space and time have been rearranged into something almost familiar from the outside and profoundly unreachable within. The collapse that makes a stellar black hole begins long before the star becomes dark. For most of its life, a massive star survives by balance. Gravity presses inward from every layer, and nuclear fusion pushes outward from the core, where light elements are fused into heavier ones and energy slowly works its way toward the surface. The star may look stable from a distance, but that stability is not stillness. It is a continuous negotiation between weight and heat, compression and radiation, inward fall and outward pressure. In a star much more massive than the Sun, this negotiation burns through fuel quickly. Hydrogen gives way to helium. Helium gives way to heavier elements. The core grows more layered and more burdened, like a furnace building its own ash into the next material it must try to burn. Each stage is shorter than the one before it, because heavier fusion reactions release less usable support and demand more extreme conditions. Near the end, the star may contain shells of different burning elements around a dense central core, while the outer layers remain enormous, bright, and unstable. The decisive problem arrives with iron. Iron is not simply another step in the same chain. Fusing iron does not release energy in the way earlier fusion stages do. It consumes energy. Once an iron-rich core forms, the star has reached a kind of thermodynamic wall. The center can no longer make enough outward pressure to support the material piled above it. Gravity, which had been present all along, no longer has an equal opponent. The collapse begins in the core, and it begins with almost impossible speed. Matter that had been held apart by heat and particle pressure is driven inward. Electrons are forced into protons, forming neutrons and releasing neutrinos, ghostly particles that stream outward through the dying star. The core shrinks, stiffens, and rebounds in a violent shock, while the outer layers begin to fall onto it. In many massive stars, this chain produces a supernova, one of the most luminous explosions in the universe. Yet the explosion is not the whole story. The light is only the visible release of a much deeper failure. What matters for a black hole is what remains at the center after the star has tried to throw itself apart. If the surviving core is not too massive, it may become a neutron star, an object where matter is packed mostly into neutrons and held up by quantum pressure. Such a remnant is already extreme beyond ordinary experience. A mass greater than the Sun can be compressed into something only the size of a city. But neutron stars also have limits. If the core is too heavy, even neutron pressure cannot stop the fall. The matter continues inward, past the last stable form that known particles can maintain. The collapsing remnant crosses its Schwarzschild radius, and the event horizon appears. From the outside, the star has left behind a stellar black hole. This is the first fully established class in the black hole hierarchy, and its origin feels almost intimate compared with the larger and stranger kinds. A stellar black hole is not an abstract relic from the beginning of the universe, or a galactic engine whose history stretches across cosmic time. It is the outcome of a star's death. The same process that once made light also made the conditions for darkness. They are born from objects that spent their lives resisting gravity, and their final form is gravity without visible resistance. Many known stellar black holes fall within a range of several to many tens of solar masses, though observations of black hole mergers have shown that heavier examples can exist. Their horizons remain comparatively small, often only tens or hundreds of kilometers across depending on mass and spin. The scale is difficult because the mass is familiar while the size is not. A black hole with several times the mass of the Sun may occupy a region smaller than a large city. A heavier one may still be no larger than an ordinary landscape. The phrase stellar black hole can make the object sound modest, but modesty only applies in comparison with supermassive giants. Locally, the gravity near such an object is severe. A passing star, planet, or cloud of gas does not need to touch the horizon to be changed by it. Tidal forces can stretch matter, because the side closer to the black hole feels a stronger pull than the side farther away. Close enough, that difference becomes destructive. Matter is pulled into streams, heated, and reshaped before any final crossing occurs. The black hole is dark at the center, but the region around it can become energetic and bright if enough material is available. The severity of the collapse also changes how time is understood near the remnant. To a distant observer, matter approaching the event horizon appears to slow and dim. Its light stretch toward longer wavelengths as gravity drains energy from the signal. For the falling matter itself, the crossing may occur without a visible marker, especially for a larger black hole where tidal forces at the horizon can be gentle at first. The same event can appear frozen near the horizon from far away, and yet proceed normally along the path of the falling object. A stellar black hole is therefore not only dense, it is a place where distance, time, and observation stop agreeing in the familiar way. The birth of such an object depends strongly on the original star. A star like the Sun will never form a black hole, because it lacks the mass needed to crush its core past the required limits. It will shed its outer layers and leave behind a white dwarf, hot and compact but not collapsed into a horizon. The stars that can make black holes begin with far greater mass. They live brighter, shorter lives, drive strong winds, and end with cores heavy enough to test the last supports of matter. Stars rich in heavier elements can lose more mass through stellar winds before they die, leaving lighter remnants, while stars with fewer heavy elements may retain enough mass to produce heavier black holes. In this way, the final darkness is connected to the star's entire life, its birth environment, composition, rotation, winds, and whether it lived alone or with a companion. The collapse is sudden, but the conditions are prepared across millions of years. Some stellar black holes may form in spectacular supernovae, with the outer layers blasted into space and enriched with elements that later become part of new stars and planets. Others may form more quietly, through direct collapse, when the core falls inward and much of the star follows without a bright explosion. In those cases, a massive star may seem simply to vanish, dimming from the sky as its light-producing layers fail. These different endings show that stellar black holes are not all born in the same manner. Some arrive with violent fireworks, some may arrive as a disappearance. Both outcomes lead to the same essential boundary, but the surrounding evidence differs, and astronomers must reconstruct the death from what remains. This is why stellar black holes are often found not by seeing the black hole itself, but by tracing the systems that survive around it. In a binary system, one star may collapse first, leaving behind a black hole that continues orbiting its companion. Later, gas from the companion can be drawn away, forming a disk and revealing the hidden remnant through high-energy radiation. In other systems, both stars may eventually collapse, creating two black holes that orbit each other in darkness until gravitational waves announce their merger. Stellar collapse, therefore, does not always end with a solitary object. It can produce a long afterlife of motion, feeding, pairing, and collision. The most unsettling feature of stellar black holes is that they are not rare exceptions produced by exotic conditions. The Milky Way likely contains a vast population of them, most invisible because they are not actively feeding. They may drift through the galaxy without glowing, without announcing themselves, without disturbing anything enough to be noticed from Earth. Their silence does not make them less real. It only means that the galaxy contains many collapsed remnants whose evidence appears only when circumstances allow. A black hole in isolation is almost perfectly quiet. A black hole with a companion can become a beacon. The object has not changed in essence, only its surroundings have given it a voice. In the hierarchy of black holes, stellar collapse provides the first grounded step because it is tied to a known and repeated life cycle. Massive stars form, burn, exhaust themselves, and die under the right conditions. Their cores pass beyond neutron support and close into horizons. The result is a compact remnant whose mass may be only a few times that of the Sun, yet whose presence rewrites every nearby path through space-time. This makes the stellar black hole both understandable and strange. Its origin belongs to stellar evolution, a process observed across galaxies. Its final state belongs to a deeper regime, where matter no longer presents itself directly, and gravity becomes the defining structure. The star that once shone by fusion ends as an object that cannot shine from within. What remains is not an empty hole in space, but a finished collapse, a place where the long struggle between pressure and gravity has ended, and gravity has kept the last word. A stellar black hole becomes visible most clearly when it is not alone. In isolation, it can drift through the galaxy with almost no signal, carrying its mass and horizon quietly through the spaces between stars. But when a black hole shares an orbit with a living star, the darkness gains an outline. The companion star does not need to fall in completely. It may only need to lose part of its outer atmosphere, drawn away by the black hole's gravity and stretched into a stream. That stream does not plunge straight across the event horizon. Matter arriving with sideways motion cannot simply drop inward. It circles, collides with itself, spreads into a flattened whirl, and forms an accretion disk. The disk is one of the most important clues in black hole astronomy, because it turns hidden gravity into measurable light. The black hole itself remains unseen, but the gas around it becomes a record of what the central object is doing. At first, the process may sound like ordinary feeding, as if matter is merely being gathered and swallowed. But the physics is more demanding than that. Gas in the disk is not a smooth river. It is turbulent, magnetized, and crowded with particles moving at different speeds. Inner material orbits faster than outer material. Friction and magnetic stresses transfer angular momentum outward, allowing some gas to lose enough orbital support to spiral inward. As it falls to smaller orbits, gravitational energy is converted into heat. The inner regions of the disk can reach temperatures of millions of degrees, hot enough to glow not mainly in visible light, but in X-rays. This is why some of the first strong black hole candidates were not found by looking for darkness. They were found as intense sources of high-energy radiation, bright against the sky in wavelengths the human eye can never see. The accretion disk is therefore a kind of translator. It takes the invisible shape of gravity near the black hole and converts it into heat, timing, spectrum, and motion. Each of those clues can be studied. The brightness may rise and fall as the flow changes. The X-ray spectrum may reveal gas heated close to the inner edge. Rapid flickering can suggest emission from a very small region, because only compact sources can vary so quickly. In some systems, the disk alternates between quiet states and sudden outbursts, as accumulated gas becomes unstable and rushes inward. The black hole is not shining like a star. It has no surface wherein falling matter crashes and radiates before stopping. Instead, light comes from the last crowded regions outside the horizon, from material struggling to shed enough motion to continue inward. That difference matters. A neutron star can also pull gas from a companion and form a bright disk, but a neutron star has a surface. Matter reaching it releases energy in a final impact. A black hole has no such surface. Past the horizon, the light-producing exchange ends. Observers must separate these possibilities by measuring mass, timing, temperature, and the behavior of the surrounding system. A dark compact object heavier than the maximum plausible mass of a neutron star becomes a strong black hole candidate. This is how a feeding system can become evidence, not just spectacle. The companion star provides the clock and the scale. As it orbits the unseen object, its light shifts slightly toward blue and red, revealing motion toward and away from Earth. From that motion, astronomers can estimate the mass of the invisible companion. If the mass is too large for a white dwarf or neutron star, the explanation narrows. The unseen object must be a black hole, unless some entirely unknown compact state is hiding there. In practice, the combination of orbital motion and X-ray emission can be persuasive. The system is not simply bright. It is bright in the way matter becomes bright when falling into a deep gravitational well, and the orbit points to a mass that ordinary remnants cannot support. Cygnus X1 became one of the classic examples of this method. It is a binary system in which a massive blue star orbits an unseen compact companion that emits strong X-rays. The evidence accumulated slowly through better measurements of the orbit, the star, and the radiation. The importance of the case was not only that one object seemed exotic, it showed that black holes could be found as working astrophysical systems, not merely as mathematical predictions or invisible endings. The feeding disk made the hidden remnant part of observational astronomy. Around such systems, the word terrifying needs careful handling. A black hole in a binary does not reach across space without limit. Its gravity follows the same broad rules as any object of the same mass when seen from far away. A star can orbit a black hole stably, just as it might orbit another star. The danger emerges through closeness and gradient, near enough. The pull on the nearer side of the companion becomes stronger than the pull on the farther side. Gas can be stripped away through a gravitational balance point between the two objects. Once transferred, it joins the disk and begins its heated inward passage. The violence is not the fantasy of a cosmic vacuum cleaner. It is the precise consequence of orbital geometry, tidal force, and lost angular momentum. What makes the scene severe is that the process can continue for long periods, slowly changing both bodies. The companion loses mass. The disk brightens and fades. The black hole gains only a small fraction of what passes through the system, because some material can be expelled in winds or jets before it crosses the horizon. In certain black hole binaries, narrow jets of particles are launched from the inner disk region, guided by magnetic fields and powered by the energy of accretion and rotation. These jets do not come from inside the horizon. Nothing can leave from there. They arise outside it, in the environment where fields, plasma, and space-time rotation interact. The existence of jets adds another layer to the evidence. A black hole may be dark at its core, but the region just beyond that darkness can organize matter into beams that travel far from the system. The object that cannot emit from within can still shape a luminous structure around itself. Observing these systems also teaches humility about interpretation. An accretion disk is not a simple signboard. It can be tilted, warped, partly obscured, or fed unevenly. The companion star may have strong winds of its own. Gas may form a hot corona above the disk, scattering photons into higher energies. Magnetic fields may drive outflows that remove material before it reaches the inner edge. Each feature changes the signal. The task is not merely to see X-rays and declare a black hole. The task is to fit the entire pattern into a physical model: the orbit, the mass, the temperature, the flickering, the spectrum, the radio emission if jets are present, and the absence of any solid surface signature. The result is a form of knowledge built from edges and consequences. The black hole is the central object, but the proof comes from everything forced to move around it. This is why feeding stellar black holes are so valuable. They allow the invisible to become almost intimate. The scale is still vast by human standards, and the physics is still extreme, but the system has rhythm. There is an orbit. There is a companion. There is gas changing state as it falls. There are outbursts, quiet intervals, and repeated measurements. The black hole is not simply a final corpse of a star. It has entered a second life as part of a binary machine, drawing matter from its surroundings and converting gravitational depth into radiation. That second life can last long enough for instruments to return again and again, watching the same object behave in different states. It also points toward larger black holes. Accretion disks around supermassive black holes operate on different scales, with much longer timescales and far greater energy, but the central idea remains related. Matter with angular momentum forms a disk. The disk heats as it moves inward. Light from the surrounding flow reveals what the horizon conceals. Stellar systems are therefore laboratories for a process that shapes galaxies at larger scale. They show the mechanics in a smaller, faster form, where changes that might take centuries near a galactic center can unfold over days, weeks, or months. In that sense, a feeding stellar black hole is both a local danger and a cosmic lesson. It demonstrates how darkness can produce brightness without contradiction. It shows that the most useful evidence may come not from the hidden object itself, but from the matter that has not yet crossed the boundary. The event horizon remains silent. The disk speaks for it. Every burst of X-rays, every shift in a companion star's motion, every flare from hot gas near the inner edge becomes part of a careful reconstruction. The black hole is known by the stress it places on its environment. It is seen through stolen atmosphere, heated spirals, and the small betrayals of light leaving the scene just before escape becomes impossible. That is the quiet power of the feeding disk. It does not remove the black hole's darkness. It gives that darkness a shape. A binary black hole does not usually begin as a pair of darknesses. It begins as a pair of massive stars, or as two black holes brought together later inside a crowded stellar environment, or as remnants shaped by the long and complicated history of a galaxy. However the pairing forms, the final system is one of the quietest and most powerful arrangements in astrophysics, two event horizons moving around a shared center of gravity, often separated by distances that shrink slowly for ages before the ending arrives with extraordinary speed. From far away, There may be no glow at all if there is little gas nearby, no accretion disk forms, no bright X-rays mark the orbit, and no obvious signal crosses the sky. The black holes circle in darkness, carrying their masses through space-time while almost nothing announces the tightening path. Yet the system is not truly silent. According to general relativity, accelerating masses disturb the geometry around them, and a close pair of black holes loses orbital energy by sending out gravitational waves. These waves are not light. They are ripples in space-time itself, a changing stretch and squeeze that moves outward at the speed of light, carrying news of a motion that no telescope could otherwise see. At first, the loss is gentle. The black holes may orbit for millions or billions of years, each circuit taking away a tiny fraction of energy. The orbit tightens, the frequency rises, the pair moves faster, the process feeds on itself, because closer objects radiate gravitational waves more strongly, and stronger radiation removes energy more quickly. What had been a long, slow inward drift becomes an accelerating spiral. In the final moments, the black holes can move at a significant fraction of the speed of light, their horizons distorted by motion and gravity, their shared space-time no longer describable as two simple objects in an ordinary orbit. The merger is not an explosion in the usual sense. There may be no fireball, no expanding shell of glowing gas, no flash that the eye could follow. Instead, the release is mostly gravitational. A portion of the total mass is converted into energy carried away by waves in space-time. For a brief interval, the power emitted as gravitational waves can exceed the combined light output of the observable stars, yet it passes through the universe almost unnoticed by ordinary matter. By the time it reaches Earth, the signal is unbelievably faint. It changes distances by less than the width of a subatomic particle across the length of a large detector arm. The severity of the event and the delicacy of the measurement sit beside each other in a way that makes binary black holes especially revealing. They are cosmic catastrophes recorded as minute tremors. The first direct detection of such a merger transformed black holes from inferred objects into sources of a new kind of astronomy. LIGO measured the passing wave from two black holes spiraling together in a distant galaxy, and the pattern matched the prediction of relativity with remarkable precision. The signal had a rising tone, often described as a chirp, because the frequency and strength increased as the orbit tightened. That sound was not sound travelling through space. It was the data translated into a form the ear could grasp. Beneath it was a mathematical signature in spiral, merger, and ring down. The inspiral carried information about the two masses and their orbit. The merger marked the point where separate horizons became one. The ring down was the settling of the newly formed black hole, vibrating briefly in the only patterns allowed by its mass and spin. This last phase is especially calm in concept, even though it follows an extreme event. A distorted black hole cannot remain distorted in arbitrary ways. It sheds irregularity through gravitational waves and relaxes toward the simple state described by relativity. The final object is larger than either original black hole, but not quite as massive as their sum, because some energy has left the system. In that difference between before and after lies the released gravitational wave energy. Nothing visible has to burn for the universe to lose mass into motion of space-time itself. Binary mergers are also important because they reveal black holes that may never feed. Before gravitational wave observatories, astronomy was biased toward black holes with bright surrounding systems stealing gas from stars, galactic centers filled with accretion, luminous disks and jets. Gravitational waves opened a darker population. They showed that black holes can be found by how they move, not by what they illuminate. This changed the known census of stellar black holes. Some detected mergers involved masses heavier than many earlier X-ray systems had suggested were common. Others raised questions about how such pairs formed and how their spins became aligned or misaligned. Each event became more than a detection. It became a clue about stellar evolution, star clusters, supernova kicks, metallicity, and the environments where compact remnants meet. There are several possible paths into a binary black hole. In one path, two massive stars are born together as a binary, evolve side by side, exchange material, survive supernovae, and eventually leave behind two black holes still gravitationally bound. That route requires delicacy inside violence. The stars must be massive enough to collapse, close enough to interact, and yet the system must not be torn apart by mass loss or asymmetric explosions. In another path, black holes form separately in a dense cluster, where many stars and remnants pass close to one another. Repeated gravitational encounters can pair two black holes and harden their orbit until gravitational radiation takes over. These different histories can leave subtle fingerprints in the merger signal, such as the distribution of masses, the orientation of spins, or the frequency of repeated mergers. A black hole that forms from an earlier merger may later merge again, especially in dense environments, creating a heavier remnant that begins to approach the uncertain territory between stellar and intermediate mass. This possibility gives binary black holes a role in the larger hierarchy. They are not only endings, they may be growth mechanisms. The collision of two stellar black holes can build a larger black hole. Repeated collisions, under the right conditions, could help create middleweight objects. The same gravitational wave signal that records destruction may therefore also record assembly. The word terrifying belongs here not because the pair threatens nearby worlds in some roaming, cinematic way, but because the merger reveals gravity in its least diluted form. Two horizons approach each other. The space between them becomes a changing landscape of curvature. The idea of separate objects loses meaning as a common horizon forms. What had been two regions from which light could not escape becomes one larger region, with its own final simplicity. The event is clean in a mathematical sense, but not gentle. It is a demonstration that space-time can ring. It can carry away energy. It can remember in a passing wave, the last fraction of a second before two invisible objects became one. Unlike light, gravitational waves pass through intervening matter almost freely. Dust does not block them. Gas does not absorb them in any ordinary way. They cross galaxies, clusters, and empty expanses with their pattern mostly intact, weakening with distance but preserving the story of their source. This makes them unusually honest messengers from hidden places, a merger behind dust, outside a luminous galaxy, or in a region with no bright gas can still be heard by the geometry of the detector. At the same time, the very weakness of their interaction makes them difficult to measure. The universe is full of vibrations, seismic noise, thermal motion, and human disturbance. A gravitational wave detector must separate a cosmic signal from all the smaller motions of Earth. The detection of binary black holes is therefore an achievement not only of theory, but of patient engineering, statistical care, and repeated confirmation. Each confirmed signal adds to a map that has no picture in the usual sense. It is a map of masses and distances, spins and rates, invisible collisions arranged across cosmic time. As the catalogue grows, binary black holes become less like isolated marvels and more like a population. They have patterns, outliers, and unanswered questions. Some mergers fit comfortably within expectations. Others press against models, suggesting unusual formation environments or previous generations of mergers. The most valuable part may be this accumulation. One gravitational wave confirms an event. Many begin to reveal a history. They show where black holes live after their stars are gone, how often they find partners, and how nature moves mass upward through collision. In the ascent through black hole types, binaries form the first true bridge between the small and the large. They begin with stellar remnants, but their mergers hint at growth beyond a single star's death. Their signal does not come from heat, surface, or light, but from motion written directly into space-time. For a long while, two black holes may circle without witness. Then, in the last tightening, the orbit becomes a message. By the time that message reaches a distant world, the black holes themselves have already become one, and the wave is only the fading record of a boundary joining another boundary in the dark. Between the familiar remnants of dead stars and the immense engines at galactic centers lies a category that should be easy to imagine and has been difficult to prove. Intermediate black holes occupy the missing middle of the hierarchy. They're expected to be heavier than ordinary stellar black holes, perhaps hundreds, thousands, or even tens of thousands of times the mass of the Sun. Yet they are far smaller than the supermassive objects that anchor large galaxies. The idea seems natural. If small black holes exist and gigantic black holes exist, then objects between them ought to exist as well. Nature, however, does not always fill a scale simply because the human mind finds the scale convenient. The missing middle is unsettling because it turns an obvious expectation into an observational problem. A black hole of intermediate mass would not necessarily have the bright surroundings of a quasar. It might not live in the crowded centre of a large galaxy. It might have no companion star close enough to feed it steadily. It might sit in a dense star cluster, in the faint core of a dwarf galaxy, or in the stripped remains of a small galaxy that has been partly absorbed by a larger one. In those settings, the black hole can be massive enough to matter and quiet enough to hide. This is why the search for intermediate black holes often feels like the search for a shadow that only appears when other objects move around it. Astronomers look not for the horizon itself, but for the slight disorder it imposes on nearby stars, gas and radiation. In a dense globular cluster, where many old stars crowd together in a compact swarm, an intermediate black hole could reveal itself through the speeds and orbits of stars near the centre. If the central stars move too quickly to be explained by visible matter alone, a hidden mass becomes plausible. Yet this method is delicate. Dense clusters contain many stellar remnants, including white dwarfs, neutron stars and smaller black holes, and a concentration of such objects can sometimes imitate the gravity of one larger black hole. The evidence has to distinguish a single central mass from a crowded collection of dark remnants. That distinction is not easy, especially when the cluster lies far away and individual stellar motions are difficult to measure. A candidate can remain suggestive for years without becoming secure. The data may point towards something heavy, but not force the conclusion that one intermediate black hole is present, that uncertainty is part of the category's identity. It is not a lack of interest. It is a lack of final separation between possible explanations. Dwarf galaxies offer another path. These small galaxies have less mass and fewer stars than giants like the Milky Way, but some appear to contain central black holes that are larger than stellar remnants and smaller than galactic titans. Such objects are important because dwarf galaxies may preserve clues from earlier cosmic times, when galaxies were smaller and black holes were beginning to grow. If a dwarf galaxy contains an intermediate black hole, it may be a living fragment of the process that later built supermassive black holes. One frequently discussed candidate, known as HLX-1, has shown unusually bright X-ray emission consistent with a black hole far heavier than ordinary stellar examples. Its brightness, distance, and behaviour have made it one of the more compelling cases. though even compelling cases must survive the pressure of alternative models and repeated observation. The difficulty is that black hole mass is rarely handed over directly. It must be inferred from luminosity, temperature, variability, surrounding stars, and the physical limits on how quickly matter can radiate while falling inward. Every inference carries assumptions. A black hole may look brighter because it is more massive, or because the inflowing matter is arranged in a way that beams radiation toward Earth, or because the system is briefly in an unusual state. The same observation can point in more than one direction. This is why intermediate black holes remain both scientifically attractive and frustrating. They are not imaginary in the casual sense. The equations allow them. Some observations strongly suggest them. Gravitational wave events have already revealed black hole remnants that begin to push into the lower edge of the intermediate range. But a large, well-mapped population is still missing. The universe has not yet offered a simple census. The stakes are higher than classification. Intermediate black holes may explain how the largest black holes grew so quickly. A stellar black hole begins with only a few to many solar masses. A supermassive black hole may contain millions or billions. Growing from one to the other by ordinary feeding is possible in principle, but difficult in the early universe, where some very massive black holes already appear when cosmic history is still young. If intermediate black holes formed early, they could serve as heavier seeds, giving growth a head start. They might arise when many stars and stellar black holes sink toward the center of a dense cluster and merge. They might form through the direct collapse of especially massive stars in low-metal environments, where weaker stellar winds allow more mass to remain until death. They might be left behind by small galaxies whose outer stars are stripped away during mergers, leaving a central black hole wandering inside a larger galactic halo. Each pathway makes different predictions about where intermediate black holes should be found, how often they should merge, and what masses they should have. The missing middle is therefore not one mystery but several joined together. It asks how stars die in extreme environments, how clusters evolve, how galaxies assemble, and how black holes gain mass without leaving much light behind. Their elusiveness also changes the emotional shape of the black hole hierarchy. Stellar black holes are severe because they compress the death of a star into a horizon. Supermassive black holes are severe because they influence entire galaxies. Intermediate black holes are severe in a subtler way. They expose a gap in the story. They suggest that an important stage of cosmic growth may be happening in places too dim, crowded, or distant for current instruments to read cleanly. The terror is not in their immediate power, but in the possibility that the universe builds its giants through hidden steps. A quiet black hole in a cluster today may be the kind of object that, under different conditions long ago, helped seed the central darkness of a galaxy. The same class that hides from ordinary surveys may have shaped the architecture of the early cosmos. Gravitational wave astronomy may become one of the cleanest ways to find them. When black holes merge, the wave pattern carries the masses of the participants and the remnant. If one member of a merger is too heavy for ordinary stellar collapse, but far below the supermassive range, the signal can point directly toward the intermediate class. Future detectors may be sensitive to mergers involving heavier black holes at greater distances, and space-based observatories could hear lower frequency waves from larger systems that ground-based instruments cannot easily detect. This matters because gravitational waves do not require the black hole to feed. They can reveal the quiet population, the objects that do not glow and do not announce themselves through gas. In that sense, the missing middle may not be truly rare. It may simply be waiting for the right kind of hearing. Until then, each candidate must be held carefully. A central mass in a globular cluster, a bright off-center X-ray source in another galaxy, a dwarf galaxy with an unexpectedly heavy core, a gravitational wave remnant that seems too large for simple stellar ancestry. None of these alone closes the case for the whole population, but together they form a pattern of pressure. The hierarchy looks incomplete without them. The growth of supermassive black holes becomes harder to understand without them. Dense stellar systems seem capable of making them, at least under some conditions. Observations keep producing hints, but not yet the broad clarity that would make the category feel settled. That is what gives intermediate black holes their particular place in the ascent. They are neither the first collapse nor the final giant. They are the unresolved passage between the two, the dark scaffolding that may connect the death of stars to the rise of galactic centers. If they are common, then much of black hole evolution has been unfolding in a hidden register. Below the brightness of quasars and above the scale of ordinary stellar remnants, if they are rare, then the universe found another route to build its largest horizons, one even stranger than the missing middle itself. Either answer changes the story. For now, the intermediate black hole remains a shape implied by several lines of evidence, a mass range with candidates rather than certainty, and a reminder that the most important parts of cosmic growth are not always the brightest. The gap is not empty, it is waiting to be resolved. Galactic centers do not always look like places of calm order. Stars crowd inward, gas streams bend under many pulls, dust hides much of the visible light, orbits overlap across scales that are difficult to picture from a quiet planetary system like the solar neighborhood. Yet inside this crowded middle, many large galaxies contain a central object whose gravity has become the simplest explanation for motions that would otherwise seem impossible. In the Milky Way, that object is Sagittarius, a star, a supermassive black hole lying at the center of the galaxy, far beyond the dust of the spiral arms and hidden from ordinary sight. It is not large by the standards of the most massive black holes known, but it is immense compared with the stellar remnants already described. Its mass is about 4 million times that of the Sun, gathered inside a region so compact that stars near it orbit as if tied to an invisible point. The evidence does not come from a surface, because there is none to see. It comes from the stars themselves, especially the bright stars close to the galactic center that swing around the unseen mass in tight, fast paths. Some make sharp turns around the center, speeding up as they pass close and then moving outward again, following the rules of gravity around a mass that cannot be a normal cluster of stars. If the same mass were made of ordinary dark objects spread through the region, the orbits would not remain so clean and compact. The center must be both very massive and very small. That combination points to a supermassive black hole. Sagittarius, a star, is therefore one of the calmest and clearest arguments for a black hole at a galactic core. It is not known because it glows with overwhelming force. Most of the time, it is relatively quiet. It feeds weakly compared with the great active galactic nuclei seen across the distant universe. But its quietness makes the evidence almost more precise. The stars around it act like test particles, mapping the gravitational field over years and decades. Their movement turns the invisible center into a measured object. The black hole is dark, but the choreography around it is readable. This is one of the strange reversals in black hole science. The most hidden object in the region can become the best defined mass, because everything nearby is forced to account for it. Supermassive black holes differ from stellar black holes not only by size but by environment. A stellar black hole is often the remnant of one massive star. A supermassive black hole belongs to the history of a galaxy. It sits within a bulge of stars, dark matter, gas, and dust, and its growth is entangled with mergers, inflows, star formation, and the long assembly of cosmic structure. The word anchor is useful only if it is used carefully. A central black hole does not hold every star in a galaxy the way a planet is held by the sun. Most stars in the Milky Way orbit because of the combined gravity of all the stars, gas, and dark matter spread across the galaxy. The supermassive black hole dominates only the innermost region, and yet its presence matters beyond that small gravitational sphere, because the energy released during feeding can affect gas across much larger distances. It is not the main mass of the galaxy, but under the right conditions it can become one of its most powerful engines. The galaxy M87 offers a different expression of the same class. Its central black hole is far more massive than Sagittarius A star, weighing billions of times the mass of the Sun. It became famous because the Event Horizon Telescope produced an image of its shadow, surrounded by a ring of emission from hot material near the horizon. The image did not show the horizon directly. It showed light bent, lensed, and organized by extreme gravity, forming a bright asymmetric ring around a central darkness. That darkness was not an empty patch on a photograph. It was the shadow cast by the black hole against glowing plasma, a visible consequence of a region from which light could not return. For a subject so often defined by invisibility, the image mattered because it gave the event horizon scale and observational form. It didn't replace the mathematics. It gave the mathematics a face made from radio waves, global instruments, and patient reconstruction. Comparing Sagittarius. A star with the black hole in M87 reveals how varied supermassive black holes can be. One sits in the center of the Milky Way and is comparatively quiet. The other sits in a giant elliptical galaxy and powers a vast jet that extends far beyond the central region. Both are supermassive. Both have horizons. Both shape nearby spacetime severely. But their surroundings are different. Their feeding histories are different, and their visible consequences differ. This matters because a black hole's influence is not determined by mass alone. It is also shaped by how much gas is available, how that gas falls inward, how rapidly the black hole spins, and how magnetic fields behave near the inner flow. A hungry black hole can become a brilliant active nucleus. A starved one can remain dim while still holding enormous mass. The event horizon defines the object, but the environment defines much of what can be observed. In a galactic core rich with gas, matter spiraling toward a supermassive black hole can release more energy per unit mass than ordinary nuclear fusion in stars. This does not happen because the black hole shines from within. It happens because gas loses gravitational energy as it moves inward through the disk, heating and radiating before some portion crosses the horizon. The innermost regions can become so luminous that the galactic nucleus outshines the combined starlight of the host galaxy at great distances. Such active nuclei become beacons from earlier cosmic times. The black hole itself remains dark, but the feeding environment becomes one of the brightest phenomena in the universe. That pairing of darkness and brilliance is central to the supermassive class. The horizon removes light from the interior. The surrounding disk can make the loss of orbital energy blaze outward. The scale also changes the character of danger. Near a small stellar black hole, tidal forces at the horizon can be extreme because the gravitational gradient is steep across short distances. Near a very large supermassive black hole, the event horizon can be so broad that the tidal difference at the boundary is milder by comparison. An object crossing the horizon of a giant black hole might not be torn apart exactly at the edge, though deeper inside the outcome remains unavoidable. This does not make the object gentle. It makes it stranger. The larger black hole can have a horizon wider than a planetary system, a boundary so expansive that crossing it might occur without a local sign while still cutting off every route back to the outside universe. The terror has shifted from tearing force to scale. A region larger than familiar astronomical structures can be arranged so that every future inside it leads inward. Supermassive black holes also raise a formation problem. No single ordinary star can collapse into millions or billions of solar masses at once. Their existence implies growth, seeding, or both. They may begin as remnants of the first massive stars, then grow by accreting gas and merging with other black holes. They may begin as direct collapse black holes, formed when huge gas clouds in the early universe fall inward without first fragmenting into ordinary stars. They may grow through repeated mergers as galaxies combine. The truth may include several channels rather than one universal path. What is clear is that supermassive black holes are not isolated curiosities placed inside finished galaxies. They are part of galaxy formation itself. Observations show relationships between central black hole mass and properties of the surrounding galactic bulge, suggesting a linked history between the growth of the black hole and the growth of the host. The relationship is not simple command from the center, but a record of shared evolution. Gas feeds stars, gas feeds the black hole. Energy from the black hole can heat or expel gas, changing future star formation. Mergers bring galaxies together and also bring their central black holes toward eventual pairing. Over cosmic time, the core becomes an archive of both accumulation and restraint. This is why supermassive black holes feel less like endpoints and more like participants in a larger system. They consume matter, but they also help regulate the conditions around them. They hide behind horizons, but their feeding can illuminate the distant universe. They are small compared with the full spread of their host galaxies, yet they mark the regions where gravity becomes most concentrated and where energy can be released with extraordinary efficiency. Sagittarius. A star shows the quiet version, a central mass mapped by patient stellar orbits and faint flares. M87 shows the monumental version, a horizon-scale shadow, and a jet connected to a far larger galactic environment. Together they make the category tangible. A supermassive black hole is not merely a larger stellar remnant, it is a different scale of cosmic consequence. A dark center whose meaning is written through stars, plasma, jets, and the slow architecture of galaxies. At this level of the hierarchy, the black hole is no longer only the aftermath of collapse. It has become part of the structure around which a galaxy remembers its history. A quasar begins as a contradiction in appearance. Through an ordinary telescope, it may look almost like a faint star, a point of light with no obvious structure, yet its distance places it far outside the Milky Way and often far back in cosmic time. For such an object to appear bright across so much space, the source cannot be an ordinary star at all. It must be the luminous center of a galaxy, powered by gas falling toward a supermassive black hole. The name once meant quasi-stellar radio source, a reminder of how star-like these objects first seemed before their true scale became clear. What matters now is not the old label, but the physical engine behind it. A quasar is not bright because light escapes from inside the black hole. Nothing crosses the event horizon and returns. It is bright because matter outside the horizon is being compressed, heated, stirred by magnetic fields, and forced to give up energy as it spirals inward. The black hole remains dark at the center, while the environment around it becomes one of the most luminous systems in the universe. This is the first key to understanding feedback. The black hole does not need to touch a whole galaxy in order to influence it. It only needs access to gas. When enough gas reaches the central region, an accretion disk forms on a scale far larger than the disks around stellar black holes, and the energy released can rival or exceed the light from all the stars in the host galaxy. The source is compact compared with the galaxy, but the power is not confined to that compact region. Radiation pours outward. Hot winds can lift material away from the disk. In some systems, narrow jets emerge along the rotational axis, extending across distances that can dwarf the visible galaxy itself. These outflows carry energy and momentum into surrounding gas, and that is where the black hole begins to shape more than its immediate neighborhood. A galaxy is not simply a collection of finished stars. It is also a reservoir of gas, and that gas is the raw material from which future stars may form. If gas cools, condenses, and fragments, new stars can be born. If gas is heated, stirred, or expelled, star formation slows or stops. Quasar feedback is the broad name for the way energy from an active supermassive black hole changes that balance. The process can be gentle over long periods or violent during a bright outburst, but the principle remains the same. A central black hole can regulate the fuel supply of its host. It can keep gas too hot to collapse, drive it into large-scale winds, or reshape the pressure of the surrounding medium. The result is not simple destruction. It is control, sometimes rough and uneven, but control nonetheless. Without feedback, models of galaxy formation tend to produce too many massive galaxies with too many young stars. The brightest galaxies in the real universe are often quieter than simple gas cooling would suggest. Their old stellar populations imply that star formation was suppressed, and active black holes are one of the main explanations for how that suppression happens. This gives supermassive black holes a double identity. They grow by consuming gas, but in growing, they can also push gas away and limit their own future feeding. The engine can starve itself. The same process that makes a quasar brilliant can also clear the material that allowed it to shine. That self-limiting behavior is one reason black holes and galaxies seem linked across cosmic time. A central black hole grows most efficiently when gas is available, and a galaxy forms stars most efficiently from the same supply. Both are fed by the same reservoir, but the black hole can return energy to that reservoir in a form that changes what happens next. In some cases, feedback may be negative, suppressing new stars by heating or removing gas. In others, it may be locally positive, compressing clouds and encouraging pockets of star formation along the edges of an outflow. Nature rarely gives a single clean answer at galactic scale. The overall effect depends on the black hole's mass and spin, the density of gas, the shape of the galaxy, the direction of jets, the history of mergers, and the timing of each active phase. A quasar does not simply switch a galaxy on or off. It enters a complicated system already in motion, then changes the possible futures available to that system. The most dramatic cases are seen in active galactic nuclei with powerful jets. These jets are not beams of light in the ordinary sense, though they shine across many wavelengths. They are streams of energetic particles and magnetic fields launched from the inner accretion region near the black hole. They move through surrounding gas, inflate enormous bubbles, and deposit energy far from the center in galaxy clusters, where many galaxies sit inside vast atmospheres of hot gas. Jets from a central black hole can carve cavities in that gas. The cavities show where energy has been delivered. Without such heating, the hot gas might cool rapidly and fall inward, producing far more new stars than are observed. With repeated jet activity, the gas can remain suspended in a warmer, less star-forming state. The black hole becomes a kind of thermostat, not by intention, but by feedback between inflow and outflow. Gas cools and moves inward. The black hole feeds and releases energy. That energy heats the surrounding gas and slows further cooling. The cycle does not need consciousness or design. It is a physical loop written in gravity, radiation, plasma, and time. Quasars also reveal an earlier universe in which galaxies were richer in cold gas and central black holes could grow rapidly. Many of the brightest quasars are seen at great distances, meaning their light began its journey when the cosmos was much younger. They show that supermassive black holes were already capable of intense feeding in the early history of galaxy formation. Their light passes across billions of years, carrying information about the black hole, the host galaxy, and the gas between galaxies. To study a quasar is therefore to study not only one active nucleus, but a whole era of cosmic growth. The brightness that first made quasars mysterious is also what makes them useful. They can act as backlights for intervening material, revealing clouds of gas through absorption patterns. They can mark the locations of young, massive galaxies. They can expose the relationship between black hole growth and the assembly of structure. The same extreme luminosity that once confused observers now provides a tool for reading the distant universe. Yet the engine remains difficult to resolve directly because it is so compact and so far away. Much of what is known must be inferred from spectra, variability, polarization, radio structure, and models of accretion. The broad emission lines in a quasar spectrum can reveal fast-moving gas near the center. The width of those lines helps estimate the mass of the black hole. Changes in brightness can suggest the size of the emitting region, because a source cannot vary coherently faster than light can cross it. Infrared emission can reveal dust warmed by central radiation. Radio observations can trace jets far beyond the nucleus. Each signal comes from a different layer of the active system, and together they build a picture of a dark central mass surrounded by an elaborate and unstable architecture of light. The terrifying aspect of quasars lies not in a sudden local threat, but in disproportion. A region no larger than a solar system or a small fraction of a galactic core can influence gas across thousands, or even hundreds of thousands of light years. Matter falling toward an invisible boundary can release enough energy to alter the fate of a galaxy. The event horizon itself remains quiet, but the approach to it becomes an engine of scale. What falls inward does not merely disappear. Before it vanishes, it can heat, radiate, drive winds, and help decide whether the host galaxy will continue forming stars or settle into older stillness. This changes the meaning of a black hole from a final sink into an active participant. It is still a place where escape ends, but around it, escape of another kind can be violently efficient radiation escaping from the disk, particles escaping in jets, gas escaping from the galaxy, and star formation escaping from the future it might have had. Quasar feedback is therefore one of the clearest examples of destruction becoming structure. The black hole consumes, but the energy released by that consumption can prevent further collapse elsewhere. It interrupts some stars before they're born. It shapes the color, size, and aging of galaxies. It may help explain why the universe contains the kinds of galaxies it does, rather than a simpler abundance of overgrown stellar cities. At this level, the black hole is no longer only a dark object at the center. It is a regulator whose influence is written in empty gas reservoirs, heated cluster atmospheres, old stellar populations, and jets that cross intergalactic space. The horror is softened by distance, but sharpened by meaning. A horizon that cannot emit light can still, through the matter gathered around it, become one of the great sculpting forces of cosmic history. The quasar shines because something is being lost. The galaxy changes because that loss does not stay local. The growth problem appears when distance becomes a clock. The farther a quasar lies, the earlier its light began its journey, and some of the brightest quasars are seen from a time when the universe was still young. Their central black holes are already enormous, sometimes holding masses of hundreds of millions or even billions of suns. That fact creates a quiet but stubborn difficulty. A supermassive black hole can grow by feeding, and it can grow by merging with other black holes. But growth takes time. Gas does not fall inward without resistance. Radiation from the hot accretion disk can push outward against the same material trying to feed the hole. Mergers require galaxies and black holes to find each other, lose orbital energy, and settle into final coalescence. Yet in the early universe, the largest black holes seem to have reached huge masses before the available time feels comfortable. They are not merely large. They are large too soon for the simplest story. The first possibility is that early black holes began as ordinary stellar remnants from the first generations of massive stars. These first stars may have been heavier than many stars forming today, because the young universe contained mostly hydrogen and helium, with very few heavier elements to help gas cool and fragment into smaller pieces. A very massive early star could die and leave behind a black hole heavier than many modern stellar remnants. That seed would then grow by accreting gas. The challenge is that even a generous stellar seed must feed efficiently and almost continuously to become a billion solar mass object in the time available. Accretion is powerful, but it is also self-limiting. As gas heats near the black hole, it radiates. That radiation pushes against incoming material. There is a characteristic balance, often described by the Eddington limit, where outward radiation pressure and inward gravity reach a kind of regulated maximum for steady spherical feeding. A black hole can exceed this under special conditions, especially if the flow is thick, uneven, or partly beamed, but the limit shows why growth is not simply a matter of letting gravity act. The black hole's own brightness can hold back its meal. This makes rapid early growth feel like a race between appetite and resistance. If the seed is small, the race is difficult. It has to begin early, remain well supplied, and avoid long periods of starvation. The host galaxy must deliver gas to the center faster than feedback drives it away. The black hole must gain mass without spending too much time in quiet intervals. Any delay matters. A star has to form, live, collapse, and leave a seed. Gas has to remain available. The seed has to sit in an environment where inflow continues. The difficulty is not that such growth is impossible in every case. The difficulty is that the most massive early quasars demand nearly ideal conditions if they began from modest stellar remnants. This is why larger seeds have become an important part of the discussion. One route is direct collapse. In this scenario, a large cloud of primordial gas avoids fragmenting into many ordinary stars and instead falls inward as a whole, forming a black hole far heavier than a single stellar remnant. Such a seed might contain tens of thousands or even more solar masses from the beginning. It would not need to climb the entire distance from a few stellar masses to a billion. It would begin halfway up the ladder, but direct collapse also requires special circumstances. Gas normally cools, breaks into smaller clumps, and forms stars. To collapse directly, it may need to stay hot enough to resist fragmentation, perhaps under the influence of strong ultraviolet radiation from nearby young galaxies that prevents molecular hydrogen from cooling the cloud efficiently. The environment has to be rare, timed, and intense. The reward is a heavy seed. The cost is that the universe must provide the right conditions before ordinary star formation takes over. Another path runs through dense stellar clusters. In a crowded young cluster, massive stars and stellar remnants can sink toward the center through gravitational interactions. Collisions and mergers may build a very massive star, which then collapses into a heavier black hole, or repeated black hole mergers may produce an intermediate mass seed. This route connects back to the missing middle. Intermediate black holes are not only an observational category between stellar and supermassive objects, they may be stepping stones in the early growth problem. A black hole of thousands of solar masses has a much easier path to the supermassive range than a remnant of only several suns. Yet cluster routes also face complications. Stellar winds may remove mass. Supernova explosions may eject remnants from the cluster. Gravitational wave recoil after mergers can kick a newly formed black hole out of the very environment where it might have continued growing. Again, Nature offers a possible pathway, but not an effortless one. The early universe itself may have helped. Gas was more abundant, galaxies were smaller and more likely to merge, and inflows along cosmic filaments could deliver material toward young galactic centers. In such conditions, black holes might have experienced episodes of rapid feeding that are harder to sustain in the more settled universe today. Some models allow super-Eddington accretion, where gas falls inward at rates above the traditional steady limit, because radiation becomes trapped in the flow or escapes more easily in certain directions. A thick disk can hide some of the radiation from the incoming gas, allowing the black hole to gain mass quickly for a time. This does not remove the problem entirely. It shifts it into questions of duration, geometry, and stability. How long can such feeding last? How often can it restart? How much mass is actually swallowed rather than expelled? The black hole can grow quickly only if the surrounding system cooperates, and galaxies are rarely simple. Observations sharpen the issue because they do not merely say that early quasars exist. They allow estimates of black hole mass, luminosity, and chemical environment. Some early quasars show heavy elements already present in their surroundings, meaning stars had formed, lived, and enriched the gas before the quasar light began its journey. The scene is not pristine emptiness with a lone black hole growing in isolation. It is an active young galaxy, already chemically evolving, already shaping gas through stars and radiation. That complexity can help by supplying dense gas and mergers, but it can also hinder growth through feedback and turbulence. The central black hole is part of a larger young ecosystem. Its mass records not only its own feeding history, but the conditions of its host. The most severe versions of the growth problem force several ideas to work together. A heavy seed may be needed but not sufficient. Rapid accretion may be needed, but not continuous forever. Galaxy mergers may help bring gas inward and combine black holes, but they can also disturb the central flow. Feedback may regulate growth, but during short phases it may not stop it completely. The early universe may have been generous with gas, but the gas still had to lose angular momentum before reaching the horizon. The problem is therefore not one missing ingredient, it is a timing puzzle. The ingredients must appear in the right order, in the right environments, for long enough to build an object whose light is later seen across nearly the whole observable history of the cosmos. This is what makes the early giants quietly unnerving. They are not theoretical possibilities waiting to be found. They are observed beacons whose existence demands an explanation. Their light says that the black hole was already there, already feeding, already massive, at a time when cosmic structure was still assembling. The universe does not wait for human models to become comfortable. It presents the finished fact first, then leaves theory to reconstruct the path. Each early quasar is a fossil of acceleration, a sign that gravity, gas, and galaxy formation found a way to move faster than the simplest picture predicts. Future observations may clarify which path dominates. More sensitive infrared telescopes can search for fainter and earlier active black holes, helping determine whether many small seeds existed or whether rare heavy seeds were more important. Gravitational wave observatories in space may one day detect mergers between massive black hole seeds from early galaxies, revealing growth directly through space-time rather than through light. Surveys of dwarf galaxies nearby may preserve clues about ancient seeding, because small galaxies that avoided major mergers could still contain black holes related to early formation channels. The answer may not be singular. Some supermassive black holes may descend from direct collapse, others from stellar seeds that fed unusually well, and others from dense cluster mergers that built intermediate stages. The population may have several origins braided together. In the hierarchy of black holes, the growth problem marks a shift from what black holes are to how quickly the universe can make them. Stellar black holes show the collapse of individual stars. Supermassive black holes show the power of galactic centers. Early quasars ask how the bridge between those scales was crossed so rapidly. The question remains open because every solution must satisfy both physics and time. A black hole cannot grow by desire. It needs mass delivered inward, radiation managed, mergers completed, and a host galaxy capable of feeding the center without destroying the conditions for feeding. The largest early black holes therefore stand like dark milestones near the beginning of cosmic history. Their presence does not break known science, but it presses hard against the simplest version of it. They show that the universe learned to build its deepest gravitational wells early, under conditions still being pieced together, and that the path from the first seeds to the first giants remains one of the most demanding passages in the black hole story. Primordial black holes begin with an inversion of the usual story. Instead of forming after stars live and die, they would have formed before any star existed, before galaxies took shape, before the universe had settled into the familiar architecture of luminous islands and dark spaces between them. They belong, if they exist, to the first instance after the Big Bang, when the cosmos was hot, dense, rapidly expanding, and still carrying tiny unevenness in its distribution of energy. In ordinary black hole formation, gravity wins after a massive star exhausts its internal support. In the primordial case, there is no star, no core, no supernova, and no long stellar life preparing the collapse. There is only the young universe itself, with some regions perhaps dense enough, for a brief moment, to fall inside their own gravitational boundary. A primordial black hole would therefore be less like a stellar corpse, and more like a fossil of extreme early conditions, a compact remnant not of death, but of beginnings. The idea is unsettling because it removes black holes from the timeline of stars. It suggests that horizons may have appeared before the first light from the first suns, when matter and radiation were still coupled in a state far removed from the present universe. The early cosmos was not smooth in an absolute sense. It had fluctuations, tiny variations that later grew into galaxies and clusters under the influence of gravity. Most of those variations were modest. They became the seeds of structure only after immense stretches of expansion and cooling. But if some rare fluctuations were much stronger than average, they might have collapsed immediately. The mass of the resulting black hole would depend on the scale of the region collapsing at that moment, because the universe was expanding rapidly. Different times corresponded to different horizon sizes, and therefore to different possible black hole masses. In principle, this allows a huge range. Some primordial black holes could be extremely small, far below the mass of any star. Others could be asteroid-like, planetary, stellar, or even larger, depending on when and how they formed. The smallest versions would not behave like permanent objects. According to Hawking radiation, black holes can slowly lose energy, and smaller black holes radiate more strongly than larger ones. A primordial black hole born with too little mass would have evaporated long before the present age of the universe, perhaps leaving only high-energy particles or radiation as a trace. Heavier ones could survive until now, drifting unseen through galaxies or intergalactic space. This makes the search partly a question of absence. If small primordial black holes once existed in large numbers, their evaporation should have left observable effects. If heavier ones are common, their gravity should betray them through lensing, motions, mergers, or their contribution to unseen mass. Each mass range faces different observational limits, and many once plausible regions have been narrowed by surveys. But narrowed is not the same as closed. The theory survives in the gaps between constraints, in the places where rare objects could still exist without violating what has been measured. One reason primordial black holes remain compelling is dark matter. Galaxies rotate as if they contain much more mass than can be seen in stars. gas and dust. Galaxy clusters bend light more strongly than visible matter allows. The large-scale structure of the universe also points toward a hidden gravitational component that does not shine or absorb light in ordinary ways. The leading explanations often involve unknown particles, but primordial black holes offer a different possibility. Perhaps some part of dark matter is not made of new particles at all, but of black holes born in the early universe. This possibility is attractive because black holes are already allowed by general relativity, and primordial formation would not require them to come from stars. Yet the idea is tightly constrained. If black holes made up all or much of dark matter in certain mass ranges, they would produce signals that surveys should detect brief brightening events as they pass in front of stars, disturbances in wide stellar systems, effects on the cosmic microwave background, or merger rates beyond what gravitational wave detectors observe. Many searches have found limits rather than confirmations. As a result, primordial black holes are not a simple solution to dark matter. They are a carefully bounded possibility, perhaps relevant in some mass windows or as a fraction of the hidden mass, but not an easy answer that dissolves the problem. Their possible role as seeds for later black holes is just as important. The early appearance of enormous quasars raises the question of how supermassive black holes became so large so soon. A primordial black hole formed with enough mass could provide a head start, especially if it settled into a young region rich with gas. It would not need a first star to be born, live, collapse, and leave a remnant. It would already exist when the first galaxies began assembling. From there, accretion and mergers could build upon a seed older than starlight. This idea does not automatically solve the growth problem, because the seed still has to find gas, remain in a growing structure, and feed efficiently. But it changes the opening conditions. Instead of asking how a small stellar remnant climbed to galactic scale quickly enough, it asks whether the early universe produced some heavier dark seeds directly. If so, the history of supermassive black holes may begin not with stellar death, but with density peaks from the first moments of expansion. Testing such a possibility requires indirect methods. One method is gravitational lensing. A compact object passing in front of a distant star can briefly magnify that star's light, not because it emits anything, but because its gravity bends the path of the starlight. Surveys watching dense fields of stars can search for these fleeting brightenings. The duration of a lensing event can reveal something about the lens mass, though position, motion, and distance complicate the inference. Another method is gravitational wave astronomy. If primordial black holes exist in pairs and merge, their mass distribution and merger history might differ from black holes formed through stars. Some detected mergers have inspired discussion, especially when masses or spins look unusual, but no signal has yet forced a primordial interpretation. A third path is cosmological. Primordial black holes could affect the cosmic microwave background, the faint afterglow from the early universe, by accreting matter and injecting energy into surrounding gas. They could also influence the formation of early structure if abundant enough. The evidence must be sought in statistics, patterns, and limits rather than in a single clear image. That makes the subject intellectually delicate. Primordial black holes are easy to overstate because they connect several profound mysteries at once: the beginning of the universe, dark matter, black hole growth, quantum effects, and the limits of observation. A single idea seems to touch all of them, but the same reach demands caution. A possibility that explains many things in outline must still pass every measurement in detail. It must not overproduce lensing events. It must not distort background radiation beyond what is observed. It must not conflict with the abundance of galaxies, the survival of stars, or the pattern of gravitational wave detections. The hypothesis remains alive not because it has already won, but because the early universe may have allowed rare outcomes that are difficult to exclude completely. Its strength is also its weakness. Primordial black holes could be nearly invisible except through gravity, and gravity can be subtle when the objects are distant, rare, or small. Their terrifying quality is quieter than that of a quasar or a merging binary. A primordial black hole does not need to blaze, feed, or collide to matter. It may simply endure, a horizon carried from the first fraction of cosmic history into the present universe. If one passed through a region of space with little matter, it could leave almost no sign. If many existed, they could contribute to the hidden gravitational scaffolding around galaxies. If some were massive enough and placed in the right early environments, they could become ancestors of the giants later observed as quasars. Each possibility turns the black hole from a final remnant into an original ingredient. That reversal changes the mood of the hierarchy. The earlier sections have followed collapse after structure stars form. Stars die. Remnants merge. Galaxies feed their centers. Primordial black holes ask whether some horizons came first, before the structures they later helped influence. They would be relics not of what the universe became, but of how uneven and compressed it might have been at the start. Their existence would make the black hole story older than stars and perhaps nearly as old as time itself. For now, they remain hypothetical, bounded by evidence but not erased by it, watched for in lensing surveys, gravitational wave catalogues, high-energy backgrounds, and the large-scale order of the cosmos. The search continues because the question is too consequential to ignore. If primordial black holes are absent, their absence still teaches physics by ruling out certain early conditions. If they are present, even as a small population, they would open a window onto an era no telescope can image directly. The shadow would become a fossil, and the fossil would point back to the first uneven breath of the universe. Hawking radiation begins with a strange refusal to let black holes remain perfectly black. In classical general relativity, the event horizon is final. Matter can cross inward, light can fail to escape, and the black hole can grow by swallowing energy from its surroundings. But nothing comes back from within. That picture is still the foundation for understanding horizons on astronomical scales. Yet quantum theory changes the question at the edge. Empty space is not truly empty in the deepest physical sense. Fields remain present, and their lowest energy state still carries fluctuations. Near an event horizon, those fluctuations are affected by the sharp division between paths that can escape and paths that cannot. Stephen Hawking's insight was that when quantum fields are considered in the curved space-time around a black hole, a distant observer should detect a faint thermal glow. The black hole behaves as if it has a temperature. It loses energy slowly, over enough time. It can evaporate. The effect is not radiation leaking out from inside the horizon. That distinction is important. Nothing travels outward after crossing the boundary. Hawking radiation is a property of quantum fields in the region outside and around the horizon, shaped by the black hole's gravity. In simplified explanations, the effect is often described with pairs of virtual particles, one falling in and one escaping. But that image is only a rough aid. The deeper point is that the definition of vacuum changes in curved space-time. What appears empty to one observer may not appear empty to another, especially near a horizon where time, gravity, and motion are arranged in an extreme way. The black hole's mass supplies the energy that appears as outgoing radiation, and as that energy is lost, the black hole becomes slightly lighter. For stellar and supermassive black holes, this loss is almost immeasurably small. Their temperatures are far colder than the cosmic microwave background, the faint afterglow left from the early universe. instead of evaporating in any practical sense today, they gain more energy from surrounding radiation than they lose through Hawking radiation. A stellar black hole would require a span of time vastly longer than the current age of the universe to evaporate. A supermassive black hole would last longer still, across timescales so extended that ordinary cosmic history becomes only an opening chapter. Stars will burn out. Galaxies will dim. New star formation will eventually fade as gas is consumed or locked away. Long after that, the largest black holes would still remain, colder and quieter, holding mass in a universe where almost everything else has grown faint. Hawking radiation therefore changes the final destiny of black holes without making them fragile in the present. It is a whisper beside the roar of accretion, a nearly undetectable mathematical glow beside the brightness of a quasar. But its meaning is enormous, because it joins gravity, thermodynamics, and quantum theory in one object. A black hole is not only a gravitational trap, it has entropy, a measure of hidden information or microscopic possibility, and its entropy is proportional not to its volume, but to the area of its horizon. That was one of the most surprising clues in modern theoretical physics. Ordinary objects store information through their internal arrangements. A black hole seems to store its thermodynamic character on a boundary. The horizon becomes more than a point of no return. It becomes a surface whose area behaves like a count of inaccessible states. The larger the horizon, the greater the entropy, the smaller the black hole, the hotter it becomes. This inverse relationship is one of the strangest parts of the theory. A large black hole is cold, a small black hole is hot. As a black hole evaporates and loses mass, its temperature rises, which makes it radiate faster, which makes it lose mass more quickly. The process accelerates. For a large black hole, the early stages are unimaginably slow. For a tiny black hole, the final stages could be brief and energetic. This is where primordial and quantum possibilities become linked to evaporation. If very small primordial black holes formed in the early universe, some may have evaporated completely by now. Their final moments, if the theory is correct, could release bursts of high-energy particles and radiation. Searches for such signatures are one way to test whether small primordial black holes ever existed. The absence of strong evidence helps constrain how many could have formed in certain mass ranges. The universe becomes a detector not only through what it shows, but through what it does not show. If too many small evaporating black holes had existed, the high-energy sky would look different. Because it does not. Some possibilities are ruled out or narrowed. The theoretical heat of a black hole also deepens the information problem. If a black hole forms from matter in a definite quantum state, then slowly evaporates as thermal radiation, what happens to the information contained in the original matter? In ordinary quantum mechanics, information is not destroyed. It may become scrambled, dispersed, or practically impossible to recover, but the underlying evolution preserves it. Classical black holes seem to hide information behind horizons forever. Hawking radiation appeared, at first, to make the issue sharper. If the black hole eventually disappears and the radiation is purely thermal, the information seems lost. That conflict is known as the black hole information paradox. It is not a minor technical puzzle. It strikes at the compatibility of quantum mechanics and gravity. Many modern ideas, from holography to subtle correlations in radiation, have emerged from attempts to resolve it. The details remain an active frontier, but the paradox has already changed how physicists think about space, boundaries, and the storage of information. In this sense, Hawking radiation is terrifying not because it makes black holes explode in the present sky, but because it refuses to let the horizon be simple. The black hole was already a limit on escape. With quantum theory added, it becomes a limit on explanation. The horizon hides an interior, carries entropy, radiates thermally, and forces a question about whether information can vanish from the universe. A place once described mainly by mass and gravity becomes a testing ground for the deepest rules of reality. The temperature is tiny for astrophysical black holes, yet the concept is severe. It suggests that even the darkest object is involved in a slow exchange with the quantum fields around it, and that absolute darkness may not survive the full accounting of physics. The future implied by evaporation is almost impossibly long. In the era when stars still shine, black holes grow more easily than they shrink. They absorb starlight, gas, dust, cosmic background photons, and sometimes other black holes. Later, after the universe expands and cools further, the background radiation will thin and fade. Only then will Hawking radiation dominate for the great black holes. Stellar black holes will evaporate first compared with the giants. But first still means after a duration that dwarfs all familiar cosmic timescales. Supermassive black holes may persist through durations written more naturally in powers than in ordinary language, although the script of their decline is simple in outline. They grow colder as long as they remain massive. They radiate faintly. They lose mass. As they become smaller, they warm. The final phase accelerates toward a last release of energy, after which the horizon is gone. What remains, if anything remains, depends on unknown quantum gravity. Some theories allow complete evaporation. Others speculate about remnants. No observation has settled this final state. The black hole's end, like its center, is hidden behind incomplete theory. The contrast between size and fate gives this type of black hole story a soft but profound arc. The largest black holes are the most durable objects known in cosmic prediction, yet they are not eternal if Hawking's calculation holds. The smallest possible black holes are the shortest lived, perhaps appearing and disappearing before they can resemble astronomical objects at all. Between those extremes lies a principle that reverses everyday intuition. Losing mass makes the black hole hotter. Becoming smaller makes it more active. The final darkness, if followed far enough, becomes heat. This does not make the horizon less real. It makes it part of a deeper thermodynamic cycle in which gravity, quantum fields, and time slowly exchange roles. The event horizon that once seemed like a perfect one-way boundary becomes a place where the universe keeps accounts in a language still not fully understood. Evaporation and heat therefore form a quieter chapter than collapse, mergers, or quasars, but they may be the most conceptually disruptive. No telescope has seen a stellar black hole fade through Hawking radiation. No detector has confirmed the final burst of a primordial black hole. The effect rests on the strong meeting of theories rather than on direct observation. Yet its influence on modern physics is immense because it gives black holes a temperature, an entropy, a lifetime, and an unresolved relationship with information. It turns them from permanent prisons into extremely slow processes. It suggests that even horizons may belong to time, and that what appears absolute on one scale may be temporary on another. In the long future, after the bright engines have quieted and the galaxies have aged into darkness, black holes may continue to speak only through this faint thermal language. Their final message would not be a blaze of accretion or a ripple from merger, but the slow accounting of energy at the edge of escape. Quantum black holes sit at the point where the familiar image of a black hole almost disappears. There may be no dying star, no glowing disk, no companion being stripped of gas, no galaxy bending around a central engine. There may be only a question about what happens when gravity is pushed down to the smallest scales that physics can meaningfully discuss. The word quantum changes the mood of the subject. It moves the black hole away from the sky and toward the foundations of theory, where space-time, particles, uncertainty, and gravity stop fitting together in the comfortable way they do in ordinary calculations. A stellar black hole is hard to see because light cannot escape from its horizon. A quantum black hole is hard to see because it may be too small, too brief, and too close to the limits of known physics to become an object in the usual astronomical sense. Its horizon, if it forms at all, would be microscopic beyond ordinary comparison, closer to the Planck scale than to any distance that matter can easily reveal. The Planck scale is not simply a very small ruler. It marks a region where quantum effects of gravity are expected to become unavoidable, where the smooth geometry of general relativity may no longer be enough. At everyday scales, space-time behaves like a continuous stage. At cosmic scales, it can curve around stars, galaxies, and black holes. At quantum scales, fields fluctuate, particles follow probabilistic rules, and measurement itself becomes part of the story. The difficulty is that no complete tested theory yet shows exactly how space-time behaves when both descriptions are required at once. A quantum black hole would live precisely in that overlap. It would be a horizon small enough that quantum uncertainty cannot be ignored, and a gravitational object intense enough that ordinary quantum field theory on a fixed background may not be sufficient. That is why these objects are less a known class and more a boundary marker. They point to the place where the map runs out. In theory, a black hole can be associated with any mass if that mass is compressed inside its own gravitational radius. For ordinary masses, the required compression is far beyond anything matter naturally achieves except in stellar collapse or extreme cosmological conditions. For tiny masses, the gravitational radius becomes so small that it approaches scales where the meaning of distance itself may have to be revised. At that point, the black hole cannot be treated as a miniature version of Sagittarius A star or Cygnus X1. It would not have a long visible life, a stable feeding disk, or nearby stars tracing its pull. Hawking radiation would dominate. The smaller the black hole, the hotter it is expected to be, and a truly microscopic one would evaporate almost immediately. Its existence would be less like a permanent object and more like a transient event. A brief concentration of energy forming a horizon, and then returning its mass to radiation and particles before any telescope could watch it in the ordinary sense. This is one reason particle accelerators entered public discussion around quantum black holes. In some speculative models with extra dimensions or altered gravity at high energies, collisions could, in principle, create microscopic horizons. The idea attracted attention because it seemed to bring black hole physics into the laboratory. But the key word is speculative. No evidence has shown that such black holes are produced in accelerators, and in standard expectations the energies required are far beyond present technology. Even in theories where they could form, they would evaporate almost instantly and would not grow by swallowing the surrounding world. Their tiny mass would make them hot, brief, and unstable. The fear that a laboratory black hole could become a planetary threat does not follow from the physics used to propose them. If such a horizon appeared, it would be a flash of new information, not a lasting abyss. The more serious terror lies elsewhere, in the way the idea forces the laws of nature to reveal their incompleteness. Quantum black holes test the relationship between three quantities that do not sit peacefully together: mass, information, and geometry. A large black hole can be described by simple external properties, yet it may have formed from an enormous variety of possible arrangements of matter. Hawking radiation suggests that it radiates thermally, but quantum mechanics demands that information should not simply vanish. For microscopic black holes, This tension is sharpened because their whole lifetime is governed by quantum gravity. There is little long classical phase in which the black hole can be treated as a smooth object, with quantum effects added gently at the edges. From formation to evaporation, the object would belong to the unknown transition zone. Does information escape through subtle correlations in the radiation? Is there a final remnant? Does the idea of a horizon itself change when the black hole is small enough? These questions cannot be answered by making the black hole smaller in imagination alone. They require a theory capable of explaining what space-time is made of, if it is made of anything at all. Different approaches offer different hints. Some versions of string theory replace point-like particles with tiny vibrating strings and suggest that black hole entropy can be counted through microscopic states in certain idealized cases. Loop quantum gravity explores whether geometry itself may have discrete structure, with area and volume built from quantum units rather than being infinitely divisible. Holographic ideas suggest that information about a volume of space may be encoded on a lower dimensional boundary, an idea partly inspired by black hole entropy itself. These frameworks are not interchangeable, and none has yet become a fully confirmed description of the real universe. Still, black holes keep drawing them together because black holes make the problem unavoidable. In most places, quantum theory and relativity can avoid a direct confrontation. In a quantum black hole, avoidance fails. Gravity is strong, scales are tiny, the horizon is central. Whatever the correct theory is, it must say what happens there. This gives quantum black holes a strange status. They may never be observed as astrophysical bodies, yet they influence how physicists think about reality. They are theoretical pressure points. A Planck-scale black hole is not terrifying because it has the mass to tear apart stars. It is terrifying because it suggests that space-time, which feels so stable at human and planetary scales, may have a deeper structure that current language only approaches indirectly. Smooth distance, continuous time, definite inside and outside. Even the permanence of information may all need refinement near this boundary. The object becomes less like a monster and more like a question made gravitational. It asks whether the universe is built on geometry, on quantum information, on something beneath both, or on a relationship that has no easy analogy. There is also a cosmological possibility. If the early universe reached energy densities high enough, microscopic black holes might have formed briefly and evaporated. Their disappearance could have contributed to backgrounds of particles or left subtle imprints in conditions that later unfolded into structure. Such ideas remain constrained and uncertain, but they show how quantum horizons connect the first instance of cosmic history with the smallest theoretical scales. The same theme returns again. Black holes are not only endings, they can also mark beginnings, transitions, and missing chapters. In the early universe, a tiny horizon might have lived for only a fraction of time, yet its significance would come from the regime it occupied. It would be a probe of conditions that no direct observation can recreate. Its absence, too, would teach something, narrowing the space of possible early physics. To speak carefully about quantum black holes is to hold back from pretending that speculation is discovery. No detector has confirmed a Planck-scale black hole. No accelerator has produced a confirmed microscopic horizon. No final theory has resolved all the questions they raise. But their scientific role is still real. They gather several hard problems into one image: how gravity behaves at quantum scales, how horizons store information, how evaporation ends, and whether space-time has a smallest meaningful structure. The category is therefore different from stellar, intermediate, and supermassive black holes. Those are objects sought in the sky, measured by stars, gas, images, and waves. Quantum black holes are sought through consistency, They are judged by whether the equations of future physics can make sense of them without contradiction. The ascent through black hole types reaches its smallest abyss here. Not the smallest in importance, but the smallest in size, duration, and certainty. The event horizon has been reduced from a galactic shadow to a nearly unimaginable boundary, perhaps so brief that the word object becomes inadequate. Yet the meaning has expanded. A quantum black hole would carry the whole conflict between the large and the small into one vanishing form. It would be gravity trying to speak in the language of quanta, and quantum theory trying to survive the presence of an edge from which classical escape is impossible. The known universe has not yet shown one directly, but the idea remains because physics has not yet explained why such a boundary should be impossible, or what must replace it if the old description fails. At this level, darkness is no longer a place in space. It is an unfinished sentence in the laws themselves. White holes enter the black hole hierarchy from the opposite direction. A black hole is defined by entry without return, a region whose horizon can be crossed inward but not outward. A white hole is the mathematical reversal of that idea, a region from which matter and light could emerge, while nothing from the outside could enter. The description sounds almost simple at first, as if the universe has drawn a mirror image of the event horizon, but the simplicity is deceptive. White holes are not observed objects in the sky. They are not known stellar remnants, not galactic anchors, not sources of gravitational waves confirmed by detectors. They arise because the equations of general relativity can be extended in ways that include time-reversed solutions, and those solutions have to be handled with care. Mathematics can describe structures that nature may never build. A white hole is one of those structures allowed in certain formal descriptions, striking in meaning, and still unsupported by direct evidence. The reason it feels so strange is that it reverses the deepest behavior of a black hole without explaining how such a reversal could begin. A black hole can form through collapse. A massive star exhausts its support, a core falls inward, and an event horizon appears. The path is severe, but it is physically motivated. A white hole has no similar known formation route. For something to emerge from a white hole, the object must already contain the conditions for outward release, yet no external matter can enter to set it up. It is as if the horizon has been placed into the universe with a past that is difficult to justify. In the time-reversed version of a collapse, the process resembles an explosion from an already existing horizon, but real cosmic processes are not usually free to run backward. Entropy, the measure associated with disorder and hidden microscopic arrangements, gives time an arrow in ordinary physics. Broken glass does not reassemble itself. Gas does not spontaneously gather into a tiny corner of a room. A collapsing star can make a black hole, but the reverse of that collapse would require an arrangement so finely tuned that it does not look like an event nature would produce easily. This is the central problem with white holes. They are not rejected because the idea lacks beauty. They are doubted because the universe would need to prepare them in an extraordinarily special way. In the most extended mathematical picture of a non-rotating black hole, the geometry can contain multiple regions, including a black hole region, a white hole region, and connections sometimes associated with wormhole-like structures. Such diagrams are useful because they reveal what the equations permit when ideal conditions are stretched to their full logical form. But ideal black holes in mathematics are not the same as astrophysical black holes in a messy universe. Real black holes form from collapse. May rotate, may feed, may be surrounded by magnetic fields and plasma, and are affected by perturbations. The full extended diagram is not necessarily a map of something physically realized. It is more like a warning about what solutions contain before the conditions of formation, stability, and cosmic history are imposed. Once those conditions matter, white holes become fragile. Small disturbances may destroy the clean structure, incoming radiation, quantum effects, or ordinary surrounding matter would disturb the horizon. Since nothing can enter a white hole by definition, any realistic environment creates tension with the ideal solution, a universe filled with background radiation, dust, stars, and gravitational waves is not a quiet stage for a perfectly isolated time-reversed horizon. Wormholes add another layer to the speculation. In some mathematical solutions, black holes and white holes appear as opposite mouths of a bridge through space-time. The idea is often described as a shortcut between distant regions, but the classical bridge in the simplest solution is not a usable tunnel. It closes too quickly, and any traveller or signal attempting to cross would not pass through in the way popular imagination suggests. Traversable wormholes, the kind that could remain open, usually require exotic conditions such as negative energy density, a form of matter or field behaviour not known to exist in the needed amounts. These requirements do not make the mathematics worthless. They make the physical claim difficult. The universe may permit equations that resemble doors, while refusing to provide the hinges that hold those doors open. White holes, in that setting, remain even more remote. The outward-facing half of a structure whose full stability is uncertain. There are also more modern speculations in which black holes might transform into white hole-like states through quantum gravity. In some proposals, the collapse does not end in a classical singularity. Instead, quantum effects at extreme density could halt the collapse and eventually produce a rebound. From the outside, because of gravitational time dilation, that rebound might appear after an immense delay. Such ideas are attempts to avoid the infinities of classical relativity and to connect black hole evaporation with a final release of information. They are intellectually serious in the sense that they address real problems, but they are not established facts. No observation has confirmed that black holes bounce into white holes. No telescope has identified a white hole remnant. No burst of radiation has been securely tied to such a transition. The speculation remains tied to the unfinished search for quantum gravity. It belongs to the same frontier as the information paradox, the end state of evaporation, and the question of whether singularities survive in a deeper theory. This is where the distinction between science and speculation has to stay clear. A stellar black hole can be inferred from the mass of an unseen companion and the X-rays of accreting gas. A supermassive black hole can be measured through stellar orbits, horizon-scale imaging, and the activity of galactic nuclei. Binary black hole mergers can be detected through gravitational waves. Intermediate black holes remain more uncertain, but they have candidates and possible gravitational wave routes. Primordial black holes are hypothetical, yet they can be constrained by lensing surveys, background radiation, and merger statistics. Quantum black holes are more theoretical still, but they arise from the known conflict between quantum mechanics and gravity. White holes stand at the far speculative edge because they are not only unobserved, but also difficult to place inside a realistic cosmic history. They are not impossible in the loose sense that mathematics never mentions them. They are unsupported in the stricter sense that nature has not shown a formation pathway or a confirmed example. The terrifying quality of a white hole is therefore different from the terror of falling into a black hole. It is not the fear of being trapped behind a horizon. It is the unease of a physical law being turned around and made almost unrecognizable. A black hole removes futures that lead outward. A white hole would remove paths that come inward. It would be a region that can influence the universe while being sealed against influence from it. Such an object would challenge the ordinary relationship between cause, environment, and response. Astrophysical objects usually carry histories written by interaction. A star forms from gas. A planet grows from a disk. A black hole forms from collapse or merging. A white hole, as commonly imagined, seems to appear with its outward contents already implied, without a known process that feeds or prepares it. That lack of a natural history is not a minor gap. It is the main reason caution surrounds the idea. Other speculative black hole relatives share this lesson. Naked singularities would expose the breakdown of classical relativity directly to the outside universe if horizons fail to hide them. Wormholes suggest shortcuts but demand stability conditions that may not be physically available. Planck-scale remnants might preserve information after evaporation, but no confirmed evidence shows they exist. Each idea grows from a genuine pressure point in theory and shows how far equations can reach beyond observation. The edge of black hole science is not a single wall. It is a layered frontier, with confirmed objects close to the centre, plausible but unconfirmed populations farther out, and mathematical possibilities at the dim outer rim. White holes belong near that rim, luminous in concept and faint in evidence. The ascent through black hole types ends here because the category forces a final act of restraint. The most unsettling idea is not always the one with the greatest mass, the brightest quasar, or the most violent merger. Sometimes it is an idea that the equations whisper, but the universe refuses to demonstrate. White holes may be mirrors that exist only in the formal symmetry of relativity. They may be hints of a deeper quantum process not yet understood. They may be impossible as long-lived natural objects in any realistic cosmos. The honest answer remains open, but not equally balanced between proof and imagination. What is known must remain separate from what is allowed, and what is allowed must remain separate from what is real. Black holes, in all their confirmed forms, already show that gravity can close escape, distort time, shape galaxies, and expose the limits of theory. White holes add one last, fragile reversal, the suggestion that a horizon might be turned inside out. Until evidence appears, they remain not cosmic objects, but boundary stones at the edge of explanation, marking the place where mathematics continues beyond the land that observation has secured. The hierarchy of black holes ends without becoming simple. At one end are the stellar remnants, born from massive stars that lose their last support and leave gravity to finish what fusion can no longer hold back. Farther along are the hidden middleweights, still difficult to confirm, carrying the possibility that cosmic growth may depend on steps not yet fully seen. At galactic centers, supermassive black holes gather the story into a larger scale, dark in themselves yet able to, like quasars, launch jets, heat gas, and influence the slow making and unmaking of stars. Beyond the established classes, the path becomes more delicate. Primordial black holes may or may not exist as relics of the first uneven moments of the universe. Quantum black holes may be less like astronomical objects than signs pointing toward a deeper theory. White holes remain mathematical reversals, elegant and uncertain, hovering at the edge where allowed ideas wait for evidence. What holds all of these together is not terror in the ordinary sense, but a quiet recognition of limits. A black hole is a place where escape ends, but it is also a place where knowledge has to become patient. The horizon hides the interior. The data comes from motion, heat, waves, shadows, and absence. Every confirmed black hole teaches something firm, and every speculative one marks a question that has not yet settled. In that way, the darkness is not empty. It is structured by law, shaped by evidence, and surrounded by signals that continue outward long after the source has vanished from view. The universe remains calm around these extremes, wide enough to hold collapse, growth, radiation, mystery, and time without hurry. The final image is not of a monster in the dark, but of gravity carried to its deepest known edge, still waiting, still measured, still unfinished,